Machine learning and gaming is a very interesting topic. This is a very fast-growing field of study, and there's a lot of potential applications. So today I'm going to talk about enabling intelligent game agents with reinforcement learning, and also what we're working on that at Unity. So a little bit about me, I'm Roping Dong. I am a machine learning engineer at Unity, and we're working on ML Agent Toolkit, which I will be talking about later. So first thing first, why are we interested in AI with games? Like what combines these two together? We know that games have been used to drive artificial intelligence research for a really long time. And today it has made a significant progress and breakthrough due to the advance in machine learning and the power of deep neural nets. So that includes like DeepMind's AlphaGo, which beats human world champion in Go. And also we see two of the most popular video games, StarCraft and Dota 2, which is once been considered impossible to solve by AI because the complexity of action space that you can do at the same time. But researchers were able to build a human-like player for that. And also, it's not just about beating human or winning a game. The hide and seek project by OpenAI shows that these agents are able to involve some interesting behavior and find some effective strategy of their own without any human supervision and intervention. And this kind of behavior is that we're interested in. So as we see how games are really pushing the boundary of these AI researches, on the other hand, these research can be very valuable in game development as they provide a way to build intelligent agents that can play this game really well. So in the game we see nowadays, pretty much everything is programmed. Like we coded everything, like the object, the behaviors in the game. But with the advance in AI researches that I just mentioned, we actually don't need to tell the agent what to do anymore. And instead, we can train the machine or the agents to learn the behavior by itself. So by doing that, we can create agents with much more complex behavior that's very hard to code. And we can create more intelligent agents to get like superhuman behaviors. So that can bring in more dynamics into your game because now that not everything is predefined even before the game starts and make your game more fun to play. So how do we create such an intelligent agent? The way we approach this problem is by reinforcement learning. So let's talk a little bit about reinforcement learning. In RL, there are two main components. One is the environment, which is the game, the scene itself, and also the agent. The agent can be anything that embedded in the environment that can interact with the environment. So at any given moment, the environment represents a certain state. That state includes all the information to describe the game. And from that state, the agent collects observations, which is usually a subset of the state, depending on the agent's observability, like what the agent can see, can perceive in the game. And so, for example, in the first-person shooter game, it can be the agent's location, velocity, camera view, or ammo count, or enemies proximity, and so on. And based on that observation, the agent can choose its action according to its policy. So the policy here is the agent's behavior, which defines how the agent acts given a situation. And that behavior is what we're interested in. And so the policy will output an action, which is, it can be like moving or jumping or shooting. And that action will interact with the environment and result in the next environment state, and also a set of rewards. These rewards will indicate the agent like how good or bad the action is under that situation. So the learning objective of the agent is to maximize the total reward it gets throughout the whole game. And so the agent will adjust its policy so that under a certain state, it will perform more the action that result in positive rewards and do less on those with negative rewards. And you can see that there's a cycle, like observation and action. So the agent keeps getting observation, doing action, and getting the next observation, and the cycle repeats. And the agent keeps updating its policy according to the reward it gets, and then it gradually learns what is the optimal behavior or optimal policy is. So this is the reinforcement learning formulation. And these intelligent agents can be very useful in many different ways. So first, it can be like player agent, which is from the player point of view of a player playing the game. So this kind of agent can be used to replace human player. And this is very useful for game testing or game balancing. So say if you want to run your game a million times to find any potential bugs or test the difficulty of each level, instead of hiring a bunch of people to do that for you, you can actually train a behavior and deploy that into thousands or even millions of agents to run that for you efficiently. Second one is non-player agents, which is the NPCs we see all the time in games. So for example, you can create a smarter enemies or a more human-like companions that interact with the player so that the game can be more interesting. And it doesn't necessarily to be something actual physical object in the game. It can be some abstract thing or even the game itself. So for example, you can use it to generate the storyline of the game dynamically based on what the player is doing in the game. Or you can create level with different difficulties based on the player's play style or like skill level. So now we have a picture of game AI and reinforcement learning. The next thing is about how Unity helps creating these intelligent agents and behaviors. So we know that Unity is one of the leading real-time 3D game development platform that allows you to create games and simulations with very rich graphics rendering and physics engine. So with Unity, you can create a complex environment for training agents that resembles the real game we play or even real world problems. So in that complex environment, the agent had to learn from a wide range of observations, including like visual signals like first-person camera view, or physics like force, velocities, accelerations, and also cognitives like strategy planning or learning the meaning of different objects in the games. So to combine the power of reinforcement learning algorithms and the creative Unity environments you made, at Unity, we build the ML Agents toolkit for that. ML Agents is the short for machine learning agents. So this is a toolkit for training and deploying intelligent agents in your Unity games. It provides an interface to integrate Unity environments with a state-of-the-art reinforcement learning algorithm to let you train machine learning agents. This is totally open source, so you can definitely check it out on GitHub after the talk, along with all these example environments. And ML Agent is not just for experience, it can be used in real game development. So here's an example of Ubisoft's paper about using ML Agents for real game development for a competitive multiplayer sports game, which is a complex, non-trivial video game. So say now you have built a Unity game, how to use ML Agent to train your own agents. How does the training look like? This process can be viewed in 3 steps. First is to integrate your game and define your agents and behaviors. The next is to actually train the agents. And finally, you embed the agent back into your game. So let's talk about the first step. So the toolkit provides the interfaces for you to set up agents and behaviors. So inside the game, you can have one or more agents, and each of them is controlled by a behavior. You can have multiple agents under the same behavior, or you can also have multiple behavior with multiple agents. And within each game, there's a academy which orchestrates the whole game running and training and controlling the behavior thing, like when to collect information, when to act. And it also has a communicator which communicates with the external Python API, which where the trainer and all the neural networks are. For the Python part, we provide our trainer with several latest reinforcement learning algorithms like PPO or SAC, or also you can also write your own trainer. So you are defining your agents and behaviors, and also you are defining the observation and action spaces for your agents. And next step is to actually train them to learn the behavior. There are two main approaches for training reinforcement learning and imitation learning. The first, reinforcement learning, the agent learns through experience, which is, like we said, the agent starts from acting randomly and exploring the games, and there will be reward that signals how the action is good or bad. And the objective is maximize the total reward it gets throughout the game. So the agent will go through a lot of trial and error, and until it finds what is good and what is bad, and until it finds the optimal policy. So it's possible that the agent can find like superhuman behavior or superhuman abilities. Here's a video of example of using reinforcement learning. So it's a game of a chicken trying to pick up gifts while avoid bumping into cars. So you can see that at first it acts pretty randomly and it's pretty bad. It doesn't really know what it's doing. After a while of training, you can see that it start to pick up something, like it start to learn like picking up gifts good and not to bump into car, but it's not perfect yet. But if you train it long enough, you can see that now it's acting like really, really good. Yeah, so that's reinforcement learning. And also another one is imitation learning. So in imitation learning, the agent learns through demonstrations. These demonstration has to be pre-recorded, and it comes from human playing the game or experts or any kind of simulations. And the agent will learn to mimic that behavior in the demonstration. So in the same graph, now the agent is not driven by the reward. Instead, it's feeding a demonstration. And its objective is to minimize the difference between its policy and the demonstration. So say that given the same observation, the agent will try to act in a similar way that the demonstration do. So it will never get something that's far better than what humans do, but it's very useful for training like human-like or say natural behaviors. Let's just see an example. Here's a car racing game. The left side is human demonstration, and right side is the machine trying to learn that. So you can see that at first it's pretty bad and it keeps bumping into the wall, but it's looking at how human could deal with these turning and accelerating. And after a while training, you can see that it starts to learn how human drive the car and start to like, and you can see that given the same observation, it acts pretty similar to what humans do. And now you can see that it's doing pretty good. Yeah. So that's training. And the final step is to embed the agent back into your game. So embedding the agent in the game is not trivial because neural network is usually very large and contains a lot of parameters and doing a lots of expensive matrix operations. So, and also your game is constrained by frame rate, rendering, and your compute resources. So at Unity, we have Barracuda, the Unity Inference Engine, which is a neural network inference library for Unity with optimized performance. So it's platform agnostic. It can run on CPU or GPU. It's optimized for different platforms. And the best thing is it's fully integrated with ML Agent. So once you train your agents, you can deploy it on all the supported platforms with the best performance. So in addition to everything I mentioned above, we also provide many other features like curricular learning or multi-brain learning. For curricular learning, it's like learning from easier tasks and then gradually increase the difficulty of the task. Also, we have adversarial self-play for a competitive multi-agent game, or we also have cooperative multi-agent. We have curiosity reward that drive when your reward is very sparse, and we can handle variable length observation, or we can have memory that sometimes your game requires you to remember what you see earlier in the game. And all these features can work together very well. So for example, you can train a competitive game using self-play, while each team is a cooperative group. And you can also add curiosity or memory to that game if needed. And for each feature, we have example environments to demonstrate that. Yeah, so at the end, I want to show you a demo that shows our recent work. We've just released a new major feature of cooperative multi-agent training. And this video is a demo of two teams playing soccer. So all the agents here are trained with the same behavior. But interestingly, they learned kind of a strategy of you have to have someone as goalie that stay close to the goal for defense. And they also learned things like pushing the ball into the corner to avoid it and go into the goal, or like you have to come to help your teammates when there's more opponents around. So this is the thing that's very interesting, like very exciting for game development. So you can imagine you can make a game which the human plays one of these agents, and you can have these smart little cubes that knows how to cooperate with you and then play the game with you. And this kind of thing can make a whole new level of NPCs that we don't see a lot in the games we have today. Yeah, so that's all for today. Thanks for coming. And you can check it out on the URL here, or you can contact us through the email.
Is it possible to do a few shots for relatively more complicated game-like environments, imitation learning with Gale and ML Agent?
Sure thing. Yes, we have Gale in ML Agent. So with Gale, you can actually, for each training session, you specify a YAML file, which is the trainer config for your training. So you can actually just say Gale and then enable that in your training. So yes.
Is there a plan to build telemetry collection tools in ML Agent to help build dashboards for audience with non-ML backgrounds?
So ML Agent is not targeted only at researchers who knows about machine learning. It's actually targeted for both researchers and game devs. And running a training with ML Agent doesn't require you to have knowledge in machine learning. So let me see the question here, like telemetry collection tools. We do have, like, in the Python console, you can monitor the training session, or also there's a tensor board that you can see the training curve, like you can see the losses going down or the rewards going up. So that's something you can monitor your training. And that should give you some context of if your training is really working, if your agent's learning something. Yeah.
By using reinforcement learning, I wonder how well can you perform a previously trained model in a different game of the same category? Is it possible some sort of transferable learning between models, or are we creating only experts in particular games or processes?
Yeah, so this is under the context of like transfer learning, and this is something that we are definitely interested in. We haven't provided a standard API for doing that, but you can definitely enable something that's similar in the game. Also, this is something that you can configure in your game. Say, like, if you can configure the observation space. So, say if you have a game, you don't train with the visual observation. You train with the actual positions or velocity of the game object in the game, so that once you like make the object have different texture or visual effects, that doesn't affect your game, and you can still run your model, and it will perform as good as before. So yeah, this is something that we are still exploring, but yes, that's definitely something that we're interested in.
How do you control the difficulty level of a trained AI player?
Um, okay, this is a good question. We don't have this kind of level controlling of an AI player right now, but like it can use to you can use the agent to test the level. Like you can put the same model under different difficulty of level, so you can see that under this level, the same agent gets 20 rewards, and in a difficulty, more difficult level, it gets like 5 of rewards, so they can like test the reward. But yeah, we were thinking of something like agent has different skill level, and that's something that's on the roadmap, but not yet.
Does ML agents use OpenAI's Gym for its environments?
We have the gym wrapper, which you can wrap the gym interface as the Unity environment. So you can use ML agent to train OpenAI gym environment. So we have that wrapper, but that's not the main focus. Yeah, but
Nice.
yeah, you can enable that. Yeah.
Is it possible to build own environments or some other games?
Of course, like you can actually just build your own game and then integrate that with ML agent. So that actually, if if you're interested, you can go to the ML agent GitHub. There's a section of like getting started. So you will start from building a very simple game, like rolling a ball, and then you can integrate that. So you build from scratch to something that the agent will learn to do the thing that you want it to do. So yes, you can build your own environment.